324. Oh no. The value of r? The Pythagorean theorem. Now we have to set it up a certain way. Who set it up? Anthony, what'd you do? Booyah! 12 squared plus r squared equals 13 squared. Anthony, why on earth did you put 13 by itself? It's the hypotenuse. Nailed it. Okay, so when we're solving this, Christina, what do we get? Mm-hmm. Okay, and what do I do next? Subtract what? 144 from both sides. Elijah, what do I get on the right side? Did you do this one? What's that? 25. Sebastian, what's the square root of 25? Question, people. Why would we call this a Pythagorean triple? Does anyone remember? Why would we call this triangle a Pythagorean triple? Zoomers, you guys can unmute and say it. Elijah just said it. It's because all of the numbers are whole numbers, right? There's no square roots. There's no decimals, okay? If they're each a whole number, it's a Pythagorean triple, okay? Of a right triangle. All right, number 2. R, and 18. There's 2 ways to do this problem, okay? Did anyone do this one? You should have gotten r equals 9 times the square root of 2. Hey, Chelsea just said it. Why is it a 45, 45, 90? Uh-huh. So then r is going to be a, right? And 18 should be the square root of 2 times r. Do you agree? All you have to do is divide by the square root of 2, divide by the square root of 2, and you get r equals 18 over the square root of 2. How on earth did we get it to look like 9 times the square root of 2? You just got to multiply the top and the bottom by the square root of 2, okay? We multiply the top and the bottom by the square root of 2, square root of 2, and you get r equals, 18 times the square root of 2 over the square root of 2 times the square root of 2, which is just 18 over the square root of 2 over 2. And these cancel and give you 9 over 1, so it's just 9 times the square root of 2. Again, since this was a free response, if you left it as r equals 18 divided by the square root of 2, absolutely right, okay? The other way you could have done this one is using the Pythagorean theorem. Let's see if we get the same thing if we use the Pythagorean theorem, okay? So a and b are my r's, so it would be r squared plus r squared equals 18 squared. Agreed? So from here, all you had to do was say r squared plus r squared, that's just going to be 2r squared equals 18 squared, which is, I think, 344. Can someone double check that? What? 324? Thank you. There we go. 324. We divide both sides by 2. We get r squared equals 162. And then we just take the square root. R equals, I have no idea of a perfect root that comes out of 162, but I do know that it's divisible by 2. So I would factor out a 2, square root of 2 times the square root of 81. Perfect square? 81. What is the square root of 81? 9. So r equals 9 times the square root of 2. Is that what we got before? Yuppers. Okay? Doesn't matter which way you did it, but you should have gotten 9 times the square root of 2 or 18 divided by the square root of 2. Chapter 10, section 1, lines and segments that intersect circles. All about circles. A lot of this vocab, actually not a lot, but a certain amount of this vocab will be review, but I want you to put at the top, this is all about your vocabulary. Okay? That is the most important part of this whole lesson. There's going to be, I'm not joking, like 15 words that we're going to have to remember about circles. Okay? All right. First slide, circles. So a circle is a set of all points in a plane that are equidistant from a given point in that plane. The center is that given point, and the radius is the segment whose endpoints are the center and any point on the circle. The plural of radius is not radiuses, it's radii, okay? You'll hear me say radii, I just want to clarify that, okay? Draw your circle on your page, and we're going to label some portions of that circle. There's going to be a center, and then we'll draw a nice radius. And then we'll label it. This is our circle. This is our center. And this is our radius. Circle, center, and radius. By a show of hands, how many people have heard of the word radius before? Okay, that's awesome. That's awesome. If you haven't, no need to worry, okay? It's just from that middle point, from that center, out to any of the endpoints, okay? And the radius exists the entire circle, and it's always going to be the same length. Sebastian, you can't see it? Like the picture? Is that better? Is it because of the glare? Yeah. Let's close these. Lauren, can you close that side for me? Just tighten the thingamajig. The shutter. Is that better? Yes, please. Thank you, Lauren. We're talking about chords, secants, diameters, and tangents. So there were 3 on the last one. These are 4 new ones, okay? A chord is a segment whose endpoints are on a circle, okay? Chord is the most basic of the segments, okay? All it says is that here's our circle. Your chord is just going to go from one end of the circle to the other. Doesn't matter if it goes through the middle. It can be as short as this little piece. It could be as long as this piece, okay? All of these are chords. All of them go from one endpoint of the circle to the other. Now, the diameter is a chord that contains the center of the circle. So it's more specific. It has to go through the middle, okay? So draw a picture of a circle. You guys are working in Notability, so you guys can draw a circle, hold your pen down or your finger, and it'll turn it into a perfect circle. Mine are not gonna look like that because I'm working in Explain Everything, not Notability, okay? All right, so a diameter, let's say this is our middle. It has to go from one end of the circle to the other, but it has to pass through the middle, okay? That is the only difference between the diameter and a chord. A diameter is a chord, but it's more specific. It has to go through the middle. Got it? So this would be a chord, right? But it would not be a diameter because it doesn't go through the middle. Okay, a secant. The only difference, guys, is this part. It's a line that intersects a circle at 2 points. So basically, it is a chord, but it's a line. It's not a segment. So it's going to go through the circle, but it's going to have arrows. It's a line, not a chord. It's not a segment. That is the only difference between a secant and a chord, is the fact that a secant is a line, not just a segment, okay? The chords, its segment ends at the endpoints of the circle. Secant does not. It keeps going on forever. All right, a tangent is a line in the plane of a circle that intersects the circle in exactly one point, called the point of tangency. okay? So let's draw a circle. And we're just gonna put a point on the edge of that circle, anywhere you want. Draw a line that intersects just that point of the circle. No other point, just that point. That is what we call a point of tangency, the red dot, and the line that intersects that circle at only one point is called your tangent. What is that? Oh.
We get shirts.
Cool.
The aliens can see us from outer space.
Got it. Thank you. Okay. Draw another point on this middle little circle. And then draw the other line that would be tangent to it, okay? So these tangent lines are like just on the very edge of the circle. They only cross the circle one time, okay? Most of the other lines will cross it twice or not cross it at all, okay? But the tangent is special because it only crosses it at one single point, okay? It's right on the edge. All right. This is just a diagram of all of those points, okay? So we've got a chord up top, we've got a diameter, we've got a secant, we've got a tangent, and then the point of tangency, okay? Any questions on any of those? Awesome. What's the difference between a secant and a chord? Secant is a line. Beautiful. You're going to say the same thing? No? What are you going to say? Yep, secants go on forever. Yep, absolutely. Okay, let's do an example. Point O is the center of the circle. Name each in the figure. What is OM? Radius. What is MN? Sebastian? It's a chord. Why? Very good. It's a segment that isn't a line, and it also goes from one end of the circle to the other. Okay, it doesn't matter which end, doesn't have to pass through the middle, so it's just a chord. Why is it not a diameter? Doesn't go through the middle. Very good. Doesn't go through our point O. Okay? All right, MN as a line. Secant. Okay? Notice the difference, right? It could be as subtle as those two arrows on the notation of the segment. Okay? MQ. That's the diameter. Okay? ML. Tangent. Now, in parentheses, put that it is a tangent segment, okay? It's not the actual tangent because the tangent must be a line, right? This is only a segment of that line. Do you guys see that? And then ML is your tangent regular because normal tangent is a line, okay? It's an actual line. And then what is point M? Point of tangency. Perfect. Points of Any questions on this first image, this first example? Are you guys with me so far? Anything confusing? And about any of the words? Okay. All right. The next thing we're going to talk about are common tangents, okay? Common tangents is take two circles and find a line that's tangent to both of them, okay? And then we're going to define there's different types of common tangent. There's an internal and there's an external one, okay? And how you figure out whether it's internal or external is you have to draw a line from the center of each circle and see if your tangent crosses that line, okay? So take a look at our first one, right? Do you agree that that line, that black line, is tangent to both of those circles? Agreed? It's tangent to each one. Now, draw a line from the center of each one and connect them. If that black line crosses the red line, it's an internal tangent. If it doesn't cross that line, we call it an external tangent. Because they do not cross. Okay? Okay, do you guys see another external tangent on this image? Is there another one, or is that the only one up at the top? Could we draw another one? Yeah? Where? On the bottom, very good, okay? There's another one right here on the bottom. Any more? I don't see any more, okay? These are the only two external tangents, all right? Okay, let's take a look at the same image, but now what we call this is an internal tangent, and I'll show you why. Draw the same centers on your circles and connect those centers. Do the lines cross? Yes. Since they cross, we call this an internal tangent. And we're going to say because I need to move that because I'm going to put something else there. We're going to write because the lines, or they cross. Okay? There is another internal tangent, and it's just right here. Oh, gosh. You guys can probably do a better job with notability. There we go. Okay? There are two internal tangents here, and they both look like that. Okay? Notice, it is a tangent because do you see how it intersects each of the circles only one time? Okay? Normally, when these circles are separated, you're going to only have two internal, two external. Okay? So on your homework, it's going to ask you to like write all the tangents that you possibly can, all the common tangents that you can. Just do your best with what it gives you. Okay? But some of them are going to have none that you can draw, and other ones are going to have 4 like this one. Some might have 3, some might only have 2. It all depends, but I want you guys to think about the 2 circles. How many lines can I draw that intersect each circle only one time? Okay? All right. Moving on. There's something else called congruent circles and concentric circles, okay? A congruent circle is a circle that has the same radius as another one, okay? So that means that they are the exact same size. All circles are the same shape, right? But these congruent circles are the same size, okay? Concentric circles are not necessarily the same size. They just have the same center, okay? So they're located at the same point in the middle, but they might be big, they might be smaller, they might be in between, different sizes, okay? So concentric means that they lie in the same plane and have the same center. So this would be a concentric circle, this one would be a concentric circle, okay? All of those have the same center, but they're not necessarily the same size. Now, if your circle is concentric and congruent, it's gonna be the same exact circle, okay? That's how we define it. So if it's the concentric and congruent, it's the same exact circle as the one before. Got it? Okay. Questions on congruent versus concentric? Do you remember how we used to have like congruent shapes too? and those were exactly the same, right? Same thing here with circles. If they're congruent, they're the same exact size, but not necessarily located in the same spot. Okay. Coplanar circles that are tangent to the same line at the same point, we call tangent circles, okay? Tangent circles. So notice, these circles intersect each other at one point, okay? So if you had circles that intersected at 2 points, they would not be tangent circles. So if you had like a Venn diagram looking double circle, this is not tangent, okay? Because they intersect here and they intersect here. They have to intersect at a single point. And if they don't intersect at all, they are not tangent either, okay? So this would also be an example where they are not tangent. I told you it's a lot of vocab, right? Okay? We've got about, I think, 10 words by now. No, more than that. Oh, we got a lot. I think we're at like 11 or 12. Questions on tangent circles? Okay. Theorem. This is our first theorem. In a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at the point of tangency. What that means, guys, is let's take BC being the tangent, right? It is going to be perpendicular to the radius as long as the radius goes to the point of tangency, okay? So you notice how B must be a shared point because that is the point of tangency on the circle. AB and AC or BC are going to be perpendicular. They're going to form a 90-degree angle, okay? And let's just set up another one. So let's put a point down here. Let's label it D. Have E be one of the points on the point of tangency. Wow, I cannot draw anything right now. There we go. That's better. Let's put E over here. And then let's draw a line or a radius from A to D. This is going to be 90 degrees as long as DE is tangent to circle A. So DE is perpendicular to AD as well. Okay? Now, this is important because we dealt all of last chapter with those right triangles, right? You're going to see a lot of right triangles coming out of the tangent line and the radius. And we're going to be able to solve them, okay? To figure out different lengths of the circle. If there's a line that's tangent to the circle, right? It's going to be perpendicular to the radius at the point of tangency. So let's go back. Theorem 10.2 just says that segments or tangent segments from a common external point are congruent. That means B is our common external point. If you drew a tangent line to one side of the circle and a tangent line to the other side, in other words, a point to A, a line to C, the distances between A and B and C and B are going to be the same, okay? So any two tangents that meet at a point outside the circle, the distance from that point to the point of tangency is going to be the same for both of them, okay? I kind of think this looks like an ice cream cone. If you turn it like sideways a little bit, doesn't it kind of look like that? That's how I remember this theorem. Like an ice cream cone, if it's not like symmetrical, if those two are not the same size, your ice cream is going to fall one way or the other, right? So just remember, in order for that ice cream cone to be perfect, just like a circle, those two lengths have to be the same amount. All right? Cool. Moving on, right? Now we got 3 examples and we're done, okay? So that's all the learning we're doing today. This is just applying all that stuff. So if OR equals 6, OT equals 8, then RT must equal what? Well, let's fill it in. So OR, it says, was 6. So let's plug that in. We've got 6 here. And we've got OT, which is 8. How would we figure out RT? Any ideas? Pythagorean theorem, right? But how do we know we can apply the Pythagorean theorem? We can only apply the Pythagorean theorem to what kind of triangles? Right triangles. How do we know this is a right triangle? Yes. The first theorem. Isn't OR a radius? Do you agree? OT is tangent to our circle, therefore this angle must be 90 degrees, okay? Must be 90 degrees. So all we're gonna do is do a squared plus b squared equals c squared. Someone set this up for me. Christian? Yep, 6 squared plus 8 squared equals, and you could use RT, you could use set a variable. Christian wanted to use x, let's use x squared. Perfect. Why is x squared alone? Hypotenuse, baby. Let's go. All right, so this is going to be 36. This is going to be 64. This is going to be x squared. We get 100 equals x squared. We take the square root, and we get x equals what, Lauren? Yes.
Isabel Mejia, please report to student services. Isabel Mejia, please report to student services. Thank you.
Okay, peeps. Now I've got a tricky question for you. What is the length of this part from the outside of the circle to point T? What is the length from the outside of the circle to point T? 5. It's not 5. You're close.
4.
4. Why?
Because the radius is going to be the same all around the circle.
Love it, the radius. So notice how RO was 6, right? R to here, just like Matthew said, has to be 6 as well. Do you guys see that? So this portion over here is just 10 minus 6, so it's got to be 4, okay? Remember that because your homework is going to ask you some questions involving that, okay? So just make sure that you remember that. That last part is going to be whatever you found for the whole hypotenuse minus that radius, okay? You confused, Chelsea? Yeah. Okay, so all I did here was any from the center, right? Going to any point on the circle, it's going to be the same because it's always going to be your radius. So this is going to be 6. This over here would be 6. This over here would be 6, right? So going from here to the outside of our circle is going to be 6. And then we just take that away from the original 10 that we had, and we get 4. Okay. You see now? Okay. All right. Example 3. Name a line tangent to circle P, but not circle O. Name the common external tangent to circle O and circle P, and then name the common internal tangent to circle O and circle P. Okay, who can do A? A line that's tangent to P, but not to circle O. What? Yeah, perfect. BO. Why? Yeah, very good. It's on the outside of P, right? So it's tangent to P, but it goes through the middle. It goes through the center of circle O, okay? Why couldn't it have been CD? Or, yeah, why couldn't it have been CD? Yeah, it's tangent to both of them, okay? It wanted one that's tangent to P, but not to O. CE and CD are tangent to both, okay? All right, name the common external tangent to CO, circle O and circle P. I think I just gave that one away. What is it? CD. CD. And this should be a line. And name the common internal tangent to circle O and circle P. What's that? CP, nope, because remember CP goes through the middle. So we have to find a line that crosses this one in red, but is tangent to both. AD, very good. Or AE, very good. AE. I think when this printed, guys, from PowerPoint, the letters got shifted around a little bit. This should be D, and this should be E. Or, I'm sorry, this should be E. All right, any questions on this one? Okay, the more we practice, the better at this stuff we will become. Right, Sebastian? All right, moving on. Last example, peeps. Circle M and circle N are tangent at P. Okay, so that means that this is a shared point by both of the circles. Okay, PR and SR are tangents to circle N. Okay, and circle N has a diameter of 16. PQ, which is this length right here, is 3. And RQ, which is this right here, is 12. And we have to find all of those segments, okay? Now, when it printed, I told you guys it kind of like shifted around a little bit, okay? What I want you guys to do is put that N is like a little bit further to the left. You can just make like a larger dot. But what has to happen is there has to be like a line here. This has to be like a straight line. And now remember, it told us that the diameter of N, so just draw any diameter through the middle, is 16 units long. And now we have to figure out PM.
Mr. Jerko,
Yeah,
would the radius be half of the diameter?
very good. The radius is just half the diameter. So, what do you think PM is, Matthew?
4.
Excellent. How'd you get that?
So, since the PN circle is half of the regular circle, it would be half the diameter.
Yep, absolutely.
The radius is half of the diameter.
Perfect. So PN, which is that full radius, right, of the original, would be half of the diameter, just like Matthew said. So this whole thing is 8, right? And then the radius of circle M is just half of that, so it would be 4, okay? MQ. MQ is now this bad boy going from here to here. How do we find that? By the way, this 4 belongs to this side. How do we find this?
Are we supposed to use the Pythagorean theorem?
You got it. Why? Why can we apply the Pythagorean theorem here?
Because we know that PN and PR are perpendicular.
Yes.
So we can apply it.
Yes. Why are they perpendicular though, guys? Who remembers? Caroline, do you remember why?
Well, PN is the radius,
Mhm.
so that's going to have, and then PR, it told us that it's a tangent, and if that one's tangent, that one's radius, and they're perpendicular.
Perfect. Because it said that PR is tangent, we know that this has to be a 90-degree angle. Very good, okay? So, what we're gonna do is we're gonna set up the Pythagorean theorem, so it's gonna be 3 squared plus 4, that's hard to see, sorry guys. 3 squared plus 4 squared is equal to, and let's just make a variable, or let's label it MQ squared, okay? The length of MQ. So we've got 9 plus 16 equals MQ squared. We get 25 equals MQ squared. we take the square root, we take the square root, and we get 5 equals MQ. We can plug that in to here, MQ equals 5. Okay, now we're looking for PR. That one's easy. What is PR, guys? Yeah, 15. You just add the 3 and you add the 12, okay? So that would be 15. What about SR? 15, why? Yes, that's the ice cream cone theorem, okay? Has to be the same as PR, okay? It has to be an even ice cream cone or else your ice cream's gonna fall over and nobody likes that, okay? So this is also 15. What about NS? Why is it 8? It's the radius, very good. So this is 8. And now for the tricky one, what is NR? That was a terribly not straight line. That's even worse, but whatever. It's not 16. How can we, it's not gonna be something very trivial. It's not gonna be something very easy. How could we figure out NR? Look at what we have right now. We're gonna have to do some calculation. Does anyone see a triangle, perhaps? What's that? Is it the what? It's not the altitude. But what, like, with which triangle? Name the 3 letters, Sebastian. NSR, okay? There's a triangle here called NSR, and I'll try to highlight it for you, but it's right here, to here, to here, to here. Now, Sebastian suggested the Pythagorean theorem, but that only applies to right triangles. Is this a right triangle? Why? Love it. We have a radius and we have a tangent segment. So this is our 90-degree angle. So if we're solving for this side over here, let's call it Y. Or I'm sorry, let's leave it as NR. Is NR a leg or the hypotenuse? Hypotenuse, okay? So we're gonna set it up as 8 squared plus 15 squared equals NR squared. Right? Do you guys agree? And this is going to be 64 plus 225 equals NR squared. And yes, you guys can still be using calculators, okay? You're going to use a calculator in chapter 10 as well. I just know my squares really well. So 64 plus 225 should give me 289. Which is NR squared. You take the square root, and you should get 17 equals NR. Boom, bada bing. Let's go.